Good morning, everyone. My name is Yusufbek Abdurakhimov. I'm a high school student from Uzbekistan, and most of my work is at the intersection of Python, AI, cybersecurity, competitive programming, and education. Today, a student can ask AI to explain a concept, write code, fix an error, summarize documentation, generate a plan, or even create a prototype. So the hard question in education is no longer only can students get information? The harder question is after AI gives them an answer, can they still build something real? This talk is not about showing projects, just to show projects. This talk is from a student's side of the table. I want to use the projects as evidence for one idea. In the age of AI, students should not stop at answers. They should learn how to turn answers into systems. My path didn't start with advanced AI or machine learning. It started with very ordinary things. Computers, Excel, small programs, simple games, websites, HTML, and then Python. Later, when I became serious about competitive programming, I moved heavily into C++ because speed and algorithms mattered there, but Python never left my path. At first, Python looked like a beginner-friendly language. Then cybersecurity changed that view. In CTF tasks, Python was not just a language for beginners, it was the fastest way to parse files, automate attacks, test assumptions, decode data, write small tools, and understand systems. Later, AI and machine learning changed it again. Python became the environment where data, models, computer vision, tensors, APIs, automation, and real users could meet in one place. That was the first serious lesson for me. Python is not powerful because the syntax is simple. Python becomes powerful when it lets a student move from learning concepts to building working systems. Around grade 8 and 9, I had to become much more self-directed. I was trying to grow in too many directions at the same time: mathematics, competitive programming, cybersecurity, AI, science, internships, and sports. It was beautiful from the outside, but from the inside it was messy. There were many moments where I was working a lot but not improving clearly. I was trying to do 10 things at once, and for some time it felt like I was not becoming excellent in any of them. That forced me to change how I learned. I started depending much more on recorded university courses, documentation, online platforms, books, and real assignments. Harvard's CS50 helped me build a stronger computer science foundation. NUS courses helped me connect Python with cybersecurity and computing. Coursera, edX, MIT materials, books, and documentations helped me go deeper. Later, AI tools made the process faster, but they didn't remove the need to think. The main change was this: I stopped waiting until someone explained everything. If I didn't understand something, I searched. If searching was not enough, I tested. If testing failed, I debugged. If debugging failed, I asked someone stronger and with more experience. That habit became more important than any single course. This is where I think AI creates both a danger and an opportunity. If a student uses AI only to receive finished answers, the student becomes faster on the surface but weaker inside. The hard parts disappear: confusion, debugging, checking assumptions, reading errors, comparing approaches, and explaining why something works. But if AI is used correctly, it can make a strong student much stronger. I use AI to compare architectures, review code, generate test cases, explain unfamiliar libraries, find edge cases, and challenge my thinking. But I still have to verify, I still have to know what to ask, and still have to decide whether the solution is correct, secure, private, scalable, and useful. So the real question is not, did the student use AI? The real question is, did AI replace the student's thinking, or did it make the student's thinking stronger? The first project I want to show is connected directly to education. It's called Uni Mentor AI. Many students want to apply to universities, but they don't know where to begin. They don't know how to compare universities, understand requirements, organize deadlines, improve essays, or build a realistic plan. UniMentor AI was used by more than 28,000 people from over 20 countries. The platform collected information about more than 1,400 universities and provided AI features such as chat mentor, university matching, essay assistance, prediction, planning, and guidance. For users, the interface needed to be simple, but behind that interface, the system depended on structured data, search, ranking, prompts, backend logic, and AI pipelines. At first, we used APIs from large AI providers that helped us move fast, but when usage grew, cost became a real engineering problem. That pushed the project toward a more serious direction, building our own education-focused LLM pipeline based on Qwen3 family. For me, this was an important lesson. It's easy to tell students use AI for learning, but the deeper lesson is students should also understand how AI tools are built, why they become expensive, why they fail, and how to make them useful for real people. This is one reason I think project-based learning matters. A student who only uses an AI tool sees the output. A student who builds an AI tool sees the data problem, the cost problem, the allocation problem, the user experience problem, and the responsibility problem. That difference is huge. The second project is HackNow. HackNow is the largest cybersecurity learning ecosystem in Uzbekistan, with tens of thousands of users every month. It was built first for Uzbekistan, with local students and local cybersecurity education in mind. Now, the plan is to move to the global market from September, fully in English, with hundreds of original tasks. HackNow also includes HackNow OS, the first cybersecurity-focused operating system from Uzbekistan. An OS here means a ready environment for practice, tools, labs, workflows, and a system where students can learn cybersecurity without spending weeks just setting up their machines. For me, cybersecurity is one of the best ways to teach students how to think, because it punishes shallow understanding very quickly. The important part is not only the platform, the important part is learning loop. A student reads a challenge, then they form a hypothesis. Maybe the issue is in a cookie, maybe it's an input validation, maybe it's an encoding, or maybe the network traffic contains the answer. Then the student writes the script, often in Python. The first attempt usually fails. That failure is not a problem, that is the lesson. The student reads the output, changes the approach, tests again, and slowly builds understanding. This is why I teach Python to students preparing for cybersecurity competitions. Not because Python magically solves everything, but because Python gives them a speed. It lets them test ideas quickly. It lets them automate boring parts and focus on reasoning. In the AI age, this is even more important. If AI gives a CTF solution and the student just copies it, almost nothing is learned. But if AI helps the student understand why one payload failed, why a parser is wrong, why a cryptographic assumption is weak, or how to write a cleaner script, then AI becomes a coach, not a shortcut. This is also where educators can make a very practical change. Instead of asking students only for the final answer, ask them for traces of their thinking. Show the failed scripts, show the error message, show the wrong assumption, show what changed between attempt 1 and attempt 5. In cybersecurity, the final flag is not the whole learning. The path to the flag is the real education. The third project moved from learning platforms into real industrial systems. This is where Python stopped feeling like only a development tool and started feeling like infrastructure. The system was built for AI safety monitoring in automotive factories. This system processed 214 camera streams around 1200 frames per second with 1.42 seconds average latency and 99.73% uptime. The problem is simple. Across hundreds of cameras, no human team can watch every stream every second and react consistently. The pipeline pulls RTSP streams, decodes video, samples frames, runs inference, tracks objects, applies temporal rules, and sends alerts to the dashboard. A single detection is never enough. In factories, one frame can be wrong because of motion blur, low light, occlusion, reflection, or camera angle. So the model output becomes a structured event, camera ID, timestamp, event type, severity, confidence, track ID, ROI, and visual evidence. For real deployment, the system also watches itself: camera heartbeat, FPS, latency, GPU load, queues, reconnects, and offline status. The privacy rule is strict: no facial recognition, no identity classification, and no employee scoring. This is the education lesson. Students should learn not only models, but the full system around the model. This is a very important difference. A notebook can show that an idea works once. A real system has to work when the camera disconnects, when the data is noisy, when the GPU is overloaded, when the network is unstable, and when the user needs an answer at the right time. So when we teach AI, I think we should teach the full pipeline earlier, not only model accuracy, also failure modes, monitoring, cost, privacy, and responsibility. The fourth example is more research-oriented. It's called Prism 2.0 and question: can a system understand human movement without storing the person as an image? Prism connects video, tensors, graph learning, and privacy in one Python pipeline. The input is ordinary video. It contains movement but also identity, face, clothing, background, and room details the model doesn't need. So the first step is a privacy boundary. The RGB image becomes 33 body landmarks. Each landmark keeps X, Y, and Z and visibility. So the first step is a privacy boundary. The RGB image becomes 33 body landmarks. Each landmark keeps X, Y, Z, and visibility. Then the skeleton is normalized. The hips becomes the center point, and body scale is used to reduce distance and body size bias. After that, Prism builds motion features, joint angles, wrist velocity, acceleration, symmetry, center of mass, and motion intensity. The signal is not the image, the signal is movement geometry. One frame shows posture, not actions. Prism keeps a 30 frame window, so the input becomes a temporal tensor. 30 frames, 33 joints, 4 channels. STGCN fits this problem because the body is already a graph. Joints are nodes, bones are edges, and action is how that graph changes over time. During training, differential privacy clips gradients, adds calibrated noise, and tracks the epsilon delta privacy cost. The goal is movement, understanding without storing the human. This is also why Python is valuable for students. With one language, a student can touch computer vision, feature extractions, tensors, machine learning, privacy, visualization, and evaluation. That doesn't mean the student understands everything immediately, but it means the student can build a pipeline, inspect each stage, and slowly turn abstract theory into something visible. The last example is not only a software project, it's about what happens when learning becomes community infrastructure. The goal was to make cybersecurity feel real and reachable for thousands of students in Uzbekistan. ICO Uzbekistan 2026 became the largest cybersecurity tournament in Uzbekistan history, with 1,500 more participants. My role was on the scientific and organizing side, and after the tournament, the work continued with top 50 finalists and national team members preparing for cybersecurity and AI security competitions. This changed the meaning of learning for me. At first, learning was personal. I wanted to become stronger. Then, projects became useful for users. Then, teaching became part of the responsibility. When students train for cybersecurity, Python is everywhere. Scripting, automation, parsing, exploit development, forensics, crypto, and analysis. But the deeper part is not syntax. Students learn how to stay with a hard problem long enough for it to become clear. That is one of the most valuable skills education can give. I also want to speak honestly about setbacks and failures. Trying to move in many directions at once created pressure and confusion. Online learning gave me more time for internships, Olympiad training, projects, and deeper study, but it was not an easy solution. I wouldn't recommend it casually to every student. It works only when there is a serious reason, strong discipline, and a life outside the screen too. One technical failure I remember clearly was connected to training on a very large video dataset. My computer estimated around 62 days of continuing training, assuming nothing failed: electricity, hardware, storage, temperature, and no crashes. At that moment, the project felt almost impossible. The first solution was not heroic. I reduced the scale, tested on smaller data, and tried to prove that the pipeline made sense before running the full version. Then my father gave me simple advice: ask. Write emails, ask companies, institutions, and people who may have hardware, data, advice, or experience. Many will not reply, some will say no, but one reply can move a project forward. The same idea helped with National Cybersecurity Olympiad Uzbekistan. We wrote to many people and institutions and to government. Support came because the idea was real, the work was visible, and we kept asking. So the practical lesson is simple. Don't wait for perfect conditions. Build a smaller proof, show evidence, and ask for help. From my own experience and from working with students in informatics, AI, cybersecurity, and national team training, there are a few things I think matter for education now. First, Python shouldn't be taught only as syntax. Syntax is the beginning. The real value comes when Python connects to files, APIs, datasets, cameras, dashboards, models, servers, logs, and users. Second, students should make more of their work public. A private project can be abandoned easily. A public project changes the standard. When the code, demo, write-up, documentation, or platform is visible, the students starts thinking differently. Third, in the AI age, grade the process more seriously than before. A final answer is now very cheap. The process is where learning is visible. Ask students to show the prompt, the failed code, the bug, the test case, the diagram, the trade-off, the source they checked, and what they changed after feedback. That is how teachers can see whether AI replaced thinking or improved students' thinking. Fourth, give students real responsibility earlier. Not motivational responsibility, real responsibility. Let them maintain a small tool, let them run a contest in school, let them teach younger students, let them publish a library, and let them build something that another person actually uses. Responsibility changes how a student learns. Fifth, teach students to work across fields. In 2026, knowing one narrow tool is not enough. A strong student may need mathematics, programming, cybersecurity, AI, writing, communication, ethics, and product thinking. Of course, depth still matters, but depth becomes more useful when the student can connect to other fields. And last one, do not underestimate students from ordinary environments. Some students have perfect schools, perfect labs, and perfect tutors, but no internal drive. Some students have ordinary conditions, but they have extreme motivation. Those students do not need empty motivation. They need standards, difficult problems, honest feedback, public work, and people who take their ambition seriously. For the next few years, I want to keep building at the intersection of AI, cybersecurity, education, and real-world systems, improving my platforms, training more students, contributing to national teams, and deepening my foundation in computer science and AI. But the main message of this talk is not about one student or one project. It's about the direction of education. AI can make students passive, or it can make them more capable than any generation before them. The difference depends on what we ask students to do. If we ask only for answers, they will optimize for answers. If we ask for systems, evidence, responsibility, and explanation, they will grow into builders. For me, Python helped make that path possible. It started with simple programs, then automation, cybersecurity, AI, real systems, and teaching. This is the kind of learning I believe we need more of. Learning where students do not only ask what is the answer, but also what can I build, who can it help, where can it fail, and what is the next honest step. That matters to me because many students from ordinary environments are capable of serious work if they are given real standards, difficult problems, honest feedback, and the chance to build something real. Thank you to PyCon Singapore for giving space to a student perspective. Especially thank you to Mr. Sung Chi for trusting me with this opportunity. And thank you to the NUS professors and educators whose teaching and materials helped me to build stronger foundation in Python, cybersecurity, and computing.